All right, carboxylic acids, esters, amides. We actually did this first slide yesterday. We talked about the acid that's in vinegar, acetic acid, and citric acid a little bit. I pointed out the 3 carboxyl groups on, that's what they're called, on citric acid. This is what makes it a carboxylic acid. And then we did a practice problem. Y'all should have these blanks already filled in. I'm not going to go back and refill it. We did a practice problem identifying esters, amides, and carboxylic acids. And this is as far as we got yesterday. So we're going to pick up with this slide right here. Okay, a few properties on carboxylic acids. By now, you guys have learned the biggest thing we're concerned about is if something can hydrogen bond or not. Okay, and how that affects the boiling point. And then we also look at the components within our molecule. Do we have nonpolar components? Do we have polar components? Okay, and how do those proportions of the molecule weigh against one another to make the overall molecule either water soluble or fat soluble? Okay, so that's exactly what we're going to do here too. So the hydrogen, by the way, on the carboxyl group is acidic. Oh, and then acid-base properties. That's another property we look at. So overall, what that means is carboxylic acids are weak acids, okay? They're not strong acids. So anybody remember the difference between strong and weak acids? What's the difference between a weak acid versus a strong acid? Someone remembers. So a strong acid, these completely disassociate. Okay, that's an E. What that means, so like HCl, hydrochloric acid, very corrosive, very strong acid. Most people are familiar with hydrochloric acid. In solution, in our bodies, wherever, it will completely disassociate. If we have 1 million molecules of HCl, it will all break up. We'll get 1 million hydrogen cations and we'll get 1 million chloride anions. Or if we had a mole of HCl, we would get a mole of H plus ions and a mole of Cl minus anions. Completely dissociates. But a weak acid is different. Weak acids partially disassociate. This is all chapter 10, by the way, if anybody needs a review on the difference between strong acids and weak acids. Now, honestly, I don't think you need to go spend a ton of time reading over chapter 10. I'm not going to like drill you on exam 2 on the difference between weak and strong acids, but we are going to talk about pKa later, briefly, for carboxylic acids, and that's only a property associated with weak acids. So this is why I'm bringing this up. So for example, if we have acetic acid, which is CH3COOH. Okay, I'm not drawing out the structure. That's just the condensed structure. This is going to partially dissociate, meaning some of it will dissociate, but you can get an equilibrium. You'll have a reversible reaction. And so you get CH3COO minus and H plus, okay? And we don't know, it's different for every acid. I can't say, oh, 50% will dissociate. We don't know, it depends. We can learn approximately how much from looking at values like pKa. And I'll get to that in a later slide. But it's just a partial dissociation. So here's what makes this H plus ion, okay? That's what acids do. They give away a hydrogen ion. This is the corrosive nature of H plus. It's the more H plus there is in a solution, the more acidic that environment is, okay? The more H plus there is, the lower the pH and the more acidic a solution is, okay? So strong acids make a whole lot of H plus, weak acids make a little bit of H plus in the solution, and that affects the corrosive properties of the solution, the acid and all that. Okay, so hydrogen bonding. We definitely, if you're looking at carboxylic acid, so let me zoom in for a second up here. we can definitely get hydrogen bonding, right? You should be able to look at this and imagine all the different ways you can get hydrogen bonding. Y'all have done a whole lab on this. You practiced drawing this in. We looked a lot with amines yesterday, how they can hydrogen bond. You know by now, the lone pairs on the oxygen, these are acceptors, all of those lone pairs. You could get 4 hydrogen bonds there. Each lone pair could participate in a hydrogen bond. And then you have this partial positive hydrogen, okay? On the, you know what, so I'm new to, I got a new app, Notability, and I'm still learning different features of it. So this partially polarized hydrogen can hydrogen bond as well. Okay, so you can get all kinds of hydrogen bonding with carboxylic acids. Okay, so what that means is compared to alkanes of similar size, for sure their boiling points are going to be a lot higher. All right. What else? So very much similar to, we talked about this with alcohols and with amines. We know that the carboxyl group on a carboxylic acid is very polar, right? We've got 2 electronegative oxygens. Okay. Now we don't always know what the rest of the molecule looks like. Okay, so the molecule could extend. I'm going to zoom back in our little picture here. We don't know what this side looks like. It could be a simple methyl group. It could extend all the way to like 8 carbons long. Okay, and an octanol type of group or an octane type of group. So we don't know what that side of the molecule looks like. So it depends. Water solubility depends on the hydrophobic and the hydrophilic portions of the molecule. What I do know, let me highlight this portion right here. Is this the hydrophobic or the hydrophilic portion? What do y'all think? Got some electronegative oxygens, very polar. So do you think that's going to be water loving or water fearing? Hydrophobic is water fearing, hydrophilic is water loving.
Is it hydrophilic?
Yes, Claire. This portion of the molecule, the carboxyl group, is very hydrophilic. Okay, now this, where I have the question mark, that's a lot where you're going to have the hydrocarbon portion of the molecule. Now you could have hydroxyl groups or bromines or chlorines bonded off of that as substituents. So there could be other polar groups introduced there. A lot of times you have a lot of carbons and hydrogens. So this is usually the hydrophobic side, okay, where you have all these carbons and hydrogens, and we just don't know how big it is. But we do know that as the hydrophobic portion increases, as it gets longer and longer, and you get more and more carbons and the carbon-oxygen ratio increases, that the melting and boiling point will also increase. Okay, why is that? Well, I'm going to look at these 3 examples down here in just a second to explain that, but let me fill in the last blank. The water solubility, however, will decrease. As you have more nonpolar, as you have a bigger and bigger nonpolar portion of your molecule, that's less and less water soluble. So, why, if the hydrophobic portion increases, why does the melting or the boiling point also increase? Okay, look at these 3 examples. 1, 2, and 3. You have I'm going to highlight the carboxyl group on each of these. Okay, that's on the right-hand side of each of these molecules. So what's different, that part's the same, right? That part's the same in every molecule. What's different is this long hydrocarbon tail. On number 3, you only have a methyl group. On number 1, you have this butyl group. On number 2, it's like octanol or bigger. I haven't counted, okay? So the length of the hydrocarbon portion. So what kind of intermolecular forces can you get? All of this, by the way, so this part is our nonpolar region. Our hydrophobic portion. Okay. So what kind of intermolecular forces occurs between nonpolar molecules? Your options are hydrogen bonding, dipole interactions, or London dispersion.
London dispersion.
Yes, Madison. So consider number 3 and number 2, because we have number 3 is the shortest, number 2 is the longest. What we're saying is that number 2, well, I don't want to give away the answer because I have a poll question on this, but consider the amount of London dispersion forces that can occur between 2 molecules of 3 just that one methyl group versus 2 molecules of 2 with these long hydroportion chains. Consider how many London dispersion forces you could get if each carbon and each hydrogen can participate in that. Okay, I'm gonna launch a poll question because I want you to answer this question. Which of the following carboxylic acids would be most soluble in water and least soluble? And then I'm gonna follow that up with which one do you think would have the highest boiling point and which one do you think would have the lowest boiling point based on this bullet point right here, what we just filled in, okay? So the first one I want you to focus on is water solubility. So let me launch the poll question. Okay, so the carboxylic acid, 1, 2, or 3, that's most soluble in water. Then on the opposite end of that, number 2, tell me which one you think is least soluble in water. And then take a stab, take a guess at what you think, which one would have the highest boiling point. Reread the blanks we filled in on that last bullet point if you need to. All right, last person. All right, we got all 7 in the poll. Share results. Okay. So here were the choices. All right, most everybody said that number 3 would be the most soluble. Okay, and that is true. Okay, because we said as the hydrophobic portion increases, water solubility decreases. All right, so that means the one with the shortest hydrophobic portion is the most water soluble. All right, so this one is definitely most water soluble. Okay. And then on the flip side of that, everybody said that number 2 would be the least water soluble, and that is true. So this one's the least soluble because the molecule is mainly nonpolar. That nonpolar portion is really, really big, and we know water's polar. Nonpolar and polar things don't mix. Okay. Now that last one with the carboxylic acid with the highest boiling point is most people said 2, and that is true because we said, I'm going to highlight it, as the hydrophobic portion increases. So 2 is the one with the longest hydrophobic portion, that the melting and the boiling point will increase. That is because this nonpolar region that I have labeled on number 2 can experience a whole lot more London dispersion forces than say molecule number 1 or molecule number 3. Does it make sense? Oh, hanging with me? Robin, you there?
Yeah, I'm here. I was actually going to say is, can we look at it like we I mean, the way I looked at it in the last chapters for like boiling point and melting point, if they had more CHs, like compared, like if they had more carbon hydrogen bonds compared, like then like an OH, obviously I knew it was, can I just compare it like that? Obviously that's what I'm doing. That was a dumb question, sorry.
No, you're good. I'm trying to make sure I understand it. Yeah, if it's got more carbons and hydrogens, okay, number 2, then it's more nonpolar, and therefore it's not as water soluble or not water soluble at all. And you can get a lot of London dispersion interactions between 2 chains like this if you had 2 molecules lined up next to each other. And so that's why we're saying it's going to have a higher melting or boiling point. Is that good?
Yeah.
Okay. I like questions.
There's also a slide that you covered, if it helps you, Robin, where we filled out these blanks and it said if it's more than 5 carbons, it can be water soluble. And if it's 1 to 3, it is. But if it's like 3 to 4, it's semi.
Yeah, that's what I was kind of talking about because I remember that and I wrote that on my note card for the test. And
if you like the carbon oxygen ratio, you could say, okay, this has a 5 carbons to 2 oxygens. Okay, this one's got like 9, I don't know exactly, but it's like 9 carbons to 2 oxygens. So you can look at the ratio between, if you like that better. Yeah.
So we can use the ratio. That's what I was.
Yep. Same principle applies here.
Okay.
Okay, it's just that instead of just an alcohol, we have this carbonyl group. Very similar though to just alcohols. Okay, how do we name carboxylic acids? I'm gonna warn you, here's my warning. We're actually gonna use a lot of common names in this chapter, okay? So I want you to get used to the common naming. You're gonna see a lot of the common names in the biochemistry chapters. I am gonna teach you the IUPAC naming, but I'm gonna focus on the common naming, okay? But we will use, we'll do a little bit of both. But I want you to know the common naming. In previous chapters, I've said, oh, there's common naming here, but I really hone in on the IUPAC naming, systematic naming. But here we'll also have the common name. So how do we name carboxylic acids? We take the E off, we name the parent, we look at the parent like alkane or whatever the root molecule is. We take the E off and we put oic acid on the end, oic acid, OIC acid. If substituents are present, we have to start numbering with the carbonyl carbon. A few of you missed points on exam 1 because of this. So remember, this is an important rule. If you have a carbonyl carbon and you're numbering and naming substituents, you've got to number that carbonyl carbon as number 1, okay? So for example, we've got 1, 2, 3 carbons here. So the alkane version of this would be propane, right? But this is a carboxylic acid. So we take the E off of propane and we make it propanoic acid. Propanoic acid. The next one over has a substituent. So how do we factor that in? Well, I'm going to look at the longest carbon chain. It's actually already numbered for us. And again, notice this carbon right here is the carbonyl carbon. Anybody confused on what I mean when I say carbonyl carbon? That's the carbon double bonded to an oxygen. That is the carbonyl carbon. So that's number 1. And then we keep numbering all the way to number 4. And we have this methyl group branched off carbon 3. So the whole name becomes 3-methyl. We know a 4-carbon chain as an alkane would be butane, but we take the E off and we put oic acid. So 3-methyl butanoic acid. Okay. Let's look at another one. We have a 3-carbon chain. That's our longest chain. So propane is the root word. It's a carboxylic acid. So propanoic acid, that is the parent name of this compound. But we have this hydroxyl group branched off of carbon 2. So it's 2-hydroxy propan, there's the name ending, oic acid. Now, this is the common name for this is lactic acid, okay? So that's why you see that sitting right above it.
Is it still the same concept of alphabetical order?
Yes, you still do substituents in alphabetical order, Maggie. Great question. Okay. This is just the disclaimer, what I already said, common namings, get ready. With common naming, there is another kind of labeling system that they throw in. And this will be especially important when we get to molecules like ATP. So they tend to use Greek letters instead of numbering 1, 2, 3. They'll use Greek letters alpha, beta, gamma. Okay. So in the common naming system, the carbons attached to the COOH group are identified with Greek letters alpha, beta, and gamma. So for example, they, instead of numbering the carbonyl carbon as number 1, they call that the alpha carbon. And the next carbon over, instead of calling that carbon number 2, they call that the beta carbon. And then if there was another carbon substituent here, which would have to make this a CH2, they would call this the gamma carbon. Okay. So that is why the only reason I'm introducing this is because it's part of the common naming system. And as you see, the common name for this is alpha keto propanoic acid. And you might be wondering, what's the alpha? Okay, the alpha just means they're identifying that the carbonyl group here, this one's a little bit of a weird one because you also have this whole carboxyl group here. So this is a very weird molecule. The next example over, I think, is actually better. They call it alpha amino propanoic acid. Okay.
sorry, I don't mean to interrupt, but I just want to get this out of the way. With the alpha, beta, and gamma, if we're more
Yeah.
comfortable writing alpha, beta, and gamma instead of drawing the sign, is that okay?
Instead of drawing what?
Instead of drawing like the sign for it, like, is it okay to write
Oh,
alpha,
if
beta?
you don't want to write the Greek symbol, you just want to write the word alpha.
Yeah,
Yeah, that's fine.
okay.
You won't see that, like, you won't see them spell out alpha. So I want you to recognize them, but if you don't like drawing Greek symbols, you can spell it out.
Okay.
So I want to clarify. I think I made it sound like, sorry. This alpha ketopropanoic acid, we have two carbonyl carbons. The one that's on the carboxyl group, this is actually the carbonyl carbon that we would label number 1. They start labeling the alpha, beta, gamma with the next carbon over. Okay, so that the next carbon over, they call that the alpha carbon. That's the next door neighbor carbon. Then one more over, they keep labeling down beta from there. So again, I think this alpha propanoic acid is a better example. We only have one carboxyl group here. I'm going to circle it. Okay, that's the carbonyl carbon. They start labeling the alpha, beta, gamma with the next carbon over. Okay. So this first carbon over, the reason they call it alpha amino, this amino group is branched off of what they're calling the alpha carbon. For us, when we number, that would typically be carbon 2. Does that make sense? I think it made it sound like the carbonyl carbon on the carboxyl group is alpha. It's not, it's the next carbon over.
Okay. So
What
start
if
with the
they're-
next one.
Yeah, start with the next one over, Maggie, and that's the alpha carbon. What if there were 2 carbons connected to the carboxylic acid? Oh, there can't, yeah, because you've got 3 bonds already taken up by oxygens. So there can only ever be 1 carbon branched off that I'm gonna put a star by that carbonyl carbon. Okay.
So are carbonyl carbons always going to be terminal?
Carboxyl groups are always terminal, just like aldehydes.
Okay.
The only carbonyl that's internal could be like, well, ketones we know are internal, but esters, we'll get to, we're actually going to hit esters and amides right after this, and those can also be internal. Okay. Continuing with some common naming, there's this table. This table will be your best friend. Okay, I'm going to allow you guys to have a note card for exam 2 as well. I would put a lot of these common names on your note card. There's just, don't waste your brain space trying to memorize all this. Okay. And then when we get, a lot of these are going to be really important when we get to like the Krebs cycle, oxalic acid, malic acid, succinic. Okay, all of that is in the Krebs cycle. So you're going to see all these again. So it would be really good to just at least recognize them and be familiar with them. Now, you can, so we said carboxylic acids can give away their hydrogens. They're acidic, right? And it's specifically the hydrogen that we said, like these hydrogens up here on the OH part. Well, they can also entirely lose their OH group. Okay, so if they lose their OH group, now they can become a substituent on other molecules. Okay, so the group left over or left unchanged once a carboxylic acid loses its OH, we name that now as a substituent. Okay, and the way they name it is they name the parent parent part of the group, and they add the ending OYL. So just the same way we would take like methane. You're familiar with this principle. It's just a little different. When I first introduced alkanes to you, I said, okay, if we start removing a hydrogen, now we have a methyl group or an ethyl group or a butyl group. You're familiar with that. We just put YL on the end. Same idea here. It's just OYL. Okay, we take off the OH group, and now we can use, these are all substituent groups that could be bonded to other molecules. So we just call them like a propanoyl group or a benzoyl group. Okay, acetic acid has to be difficult. It's an exception. There's no O. Okay, so like it's not acetyl, it's just acetyl, just like a methyl group or an ethyl group. I don't know why. So that's the only exception though, is you call this an acetyl group. I would memorize that. That's going to be really, really important in so many pathways. that we get to in the coming chapters. Okay, know what an acetyl group is. I don't want you to be confused when I say, okay, an acetyl group is transferred, blah, blah, blah. It's a CH3 with a carbonyl carbon. Okay. I think that's all I have for this slide. I wanted to finish this out. So this is methane. When we take a hydrogen off and we just have CH3. We call this a methyl group. Okay. So the idea is similar with the carboxyl substituents here. All right, let's do some practice. So I want you to give the systematic and the common name for this compound. This is a carboxylic acid, and I see two substituents here. Do the systematic name first, and then we can work through the common naming together. So take a look at this and try to name it systematically. Anybody want to throw out a suggestion for the systematic name? How many carbons are on our longest chain here?
4.
4. So instead of butane, it'll be butanoic.
And then I did 3 hydroxy.
Well, oh,
Okay, so that's the root parent name. Now we gotta, yes, we have to do the substituents. Who said they did 3 hydroxy?
Abby.
Okay, so that's carbon 1, 2, 3, and 4. So yeah, we got hydroxy off of number 3, and we have a methyl group. And if you're looking at these two, which one has alphabetical priority? The hydroxy group. So that's why we gotta do it first. So this will be 3 hydroxy, and then what?
2 methyl.
Yep, -2 methyl. 3 hydroxy, 2 methyl, butanoic acid. I don't know about you guys, but if it got much more complicated than this, you could count me out. I'll be darned that we are moving. I'll be glad we're moving on with naming after this. So now the common name. I think you should see the previous slide. There's a common name for a 4-carbon carboxylic acid. Anybody know what that is or see it?
Butyric.
Yeah, so instead of butanoic, it's butyric. It's this one right here, butyric. BUTYRIC. So that's the root common name. So we're going to go and write that. Now we have to use the Greek letters for the substituents. So
The alpha beta.
yes, we're gonna, this is our carbonyl carbon. So we go 1 over and we call this alpha. We go 1 more over, we call this beta. And then this one would be the gamma. So instead of 3 and 2, we'll just say it's beta. I better write small. Beta hydroxy. And then alpha methyl butyric acid. Okay. So there's that practice. Now we're going to draw the structure of the following acids: 2-ethyl 3-hydroxy hexanoic acid, 2-ethyl 3-hydroxy hexanoic acid. So this hex right here, that's the thing I look at first. That means there's 6 carbons. It's a carboxylic acid, so my COOH group is on the very end. I don't care what end you put it on. You can put it at the right or the left. I always like to draw mine like this, with the carboxyl group on the right side, but it's okay if you put it on the left too. So I'm going to draw that here. And I've got 6 carbons. This one is the first one. So carbon, carbon, 3, 4, 5, 6. Now we have 2 ethyl. So this is carbon 2. So I have an ethyl group. I'm just going to branch it off like that, a line structure. And then we have 3 hydroxy. So 1 more carbon over and we got an OH group. Okay. And the rest of these, this is CH2, CH2, and this is CH3. And we should have a hydrogen also on that one, and a hydrogen also on that one. If you draw the line structure, you do not have to draw all those hydrogens in. And I will say too, I saw this some on the homeworks, and I know you see me do it, and so on the homework it's fine for me, but on an exam, if you're going to draw a structure out, I want you to draw the entire thing accurately. So if you're going to do the line structure, commit to a line structure. Don't draw the hydrogens in. Draw it as an accurate line structure. But if you're going to draw a Lewis structure or a condensed structure, you've got to include hydrogens. Okay, so if you're going to draw a structure out in a Lewis structure or condensed structure form, don't just draw the carbons. I know that we know where the hydrogens go, but draw them in, okay? Don't just leave a structure like this devoid of its hydrogens if you're going to draw it in a condensed or Lewis structure form. All right, M-nitrobenzoic acid. M-nitrobenzoic acid. Okay, so benzoic is right here. So you'll draw this, and then I put the little figure down here so we can remember ortho, meta, and para. So we got a COOH group. And by the way, I want to point this out. Whoops. Let me redraw this really quick. What you see on the table is it says COOH, like this. You will commonly see this, okay? This and this are the same thing. It just, one is not showing you the binds and one is. But if we're going to have M-nitro, we know M is the meta. That is if this is carbon 1, this is carbon 3, that's a 1,3 spacing around the aromatic group. So it doesn't matter if I go right here or right here, either one could be considered 3. It doesn't matter if you go counterclockwise or clockwise, but we just got to pick one. So we'll say here, and it's nitro, NO2. So that is a meta spacing nitrobenzoic acid. Questions on that? Okay. There are times in molecules. So what is a dicarboxylic acid? There are times where you can have 2 carboxyl groups. Okay, citric acid. That was on one of the first slides. I pointed out 3 carboxyl groups all in the same molecule. So if there's 2 carboxyl groups, we call it a dicarboxylic acid. If there's 3 carboxyl groups, we call it a tricarboxylic acid. We just use the prefix di and tri, so forth. Now, we have specific naming though for dicarboxylic acids, all right? We have the name ending dioic, all right? I really don't want you to, honestly, I'm probably not going to ask any dicarboxylic acid stuff on the exam. The only reason I want you to not be thrown off by this is because you're going to see these intermediates in like the Krebs cycle, citric acid cycle. So again, oxalic acid, The way they name this is 2 carbons in the middle. So the root parent alkane is ethane. So they name it as ethane dioic acid. Succinic acid has 1, 2, 3, 4 carbons in the middle between the 2 groups. So the root parent alkane there is butane. So they literally name it butane dioic acid because you've got butane and then you have these 2 carboxyl groups on the ends. All right, so on and so forth. Pentane dioic acid, and then it has its own common name. We're really used to dropping the E and then adding that name ending on, but here they retain the E. They don't lose the E. It's the full ethane, butane, pentane, and then just dioic, okay? Okay. I'm not gonna get into that. We'll move on. Okay, so that's carboxylic acids. Now we're gonna talk about esters, then we're gonna talk about amides, and then we're gonna look at how do we make esters and how do we make amides, because esters and amides are derivatives of carboxylic acids. Y'all know what I mean when I say derivative? Like you start with a carboxylic acid and then you customize that to get your ester or your amide. Okay, they are formed from carboxylic acid. So we're going to look at the properties of esters and amides, how to name them, and then we're going to look at how do we make esters and amides from carboxylic acids and those reactions. Okay, so an ester looks like this. We've got this carbonyl group, but instead of an OH right here, we have an O with some sort of alkyl group. It could be wildly different. It could be a methyl group is the simple one. It could be an ethyl, a butyl. It could be a whole cyclic ring. But as long as you have some sort of alkyl group on the other side of this carbon-oxygen bond, that is an ester, and that other oxygen is bonded to a carbonyl carbon. We abbreviate this. So we abbreviate this CO, that's the carbon-oxygen double bond part. And then the OR is how you know it's an ester. Okay, the R stands for the alkyl group, some sort of carbon substituent. Okay, these are compounds formed when the OH of a carboxylic acid is converted to an OR, some sort of alkyl group. And I'm just putting the prime there to indicate that this R group does not have to be the same. So we got O and then we got some sort of R group. It does not have to be the same as whatever the R group on this side is. There's another carbon group on that side. And those 2 things don't have to be the same. They could be different. So that's why I put a prime on one and no prime on the other. Okay, so unlike carboxylic acids, esters cannot hydrogen bond with themselves, but only with water. Okay, let's think about that for a second. Remember, hydrogen bonds are broken down into acceptors and donors. So if you are looking closely at an ester, I'm going to erase all my scribbles on this. Here's what we see. I'm going to zoom in. All these acceptors, no donor. So that is why they cannot hydrogen bond with themselves. They can only hydrogen bond with water. Okay. So because of that, if you're comparing esters to carboxylic acids, okay, the boiling points for esters are going to be lower than carboxylic acids. Questions on that? Anybody need me to draw anything out or really look into that? Carboxylic acids have both donors and acceptors, so they can hydrogen bond with themselves. Esters only have acceptors, so they cannot hydrogen bond with themselves. So therefore, they will experience mostly dipole interactions, not hydrogen bonding, just with themselves. Additionally, another property about esters, they are not acidic or basic. They don't have an acidic hydrogen. Okay, none of these hydrogens on the carbons are positively polarized. So therefore, they're not acidic, they're not basic. All right. Depending on the size of the ester, so depending on these alkyl groups that I'm going to highlight right here and right here, that is where the molecule could become very hydrophobic if those are really big carbon groups. But if they're small, like just 2 methyl groups or an ethyl and a methyl group, then the ester is relatively polar and soluble in water. Okay, so that's why we're just saying smaller molecular weight esters are somewhat soluble in water. Okay. That sounds kind of vague though. So again, it just depends on how big those alkyl groups are. I'm not gonna, on the exam, I'm not gonna split hairs on that and try to like trick you. So just go with what it says off the page. Okay, how do we name them? We name them with this name ending ATE8. So it's a 2-word naming system. The first word is you're going to name the alkyl group, the R prime group, the part that is the S that makes it the ester. You're going to name that, and then you're going to name the parent acid that this ester is formed from. Okay. So you'll consider, okay, what carboxylic acid did I have to get this ester? And you'll change the name ending from ic acid to A. For example, let's look at this right here. This part of the molecule highlighted in blue, this is from acetic acid. If you could imagine just an OH, that would be acetic acid. But now we have an ester, okay? And this part is an ethyl group. And don't worry about that. It says it's from ethyl alcohol. We'll get to that when we get to esterification, formation of esters. But we have this ethyl group. So we're going to name this part first, and we name this part second. So it's ethyl acetate, okay? See the name ending, ATE, right here. Instead of acetic acid, it becomes acetate. And that's the common naming, acetic acid. All right, let's look at another example. This, if it's a carboxylic acid, is benzoic acid. And the substituent that makes it an ester is just a methyl group. So we combine the 2 words, we name the alkyl group on the ester part first, methyl. And then benzo, instead of benzoic acid, we call it benzoate, methyl benzoate.
I have a question.
Yes, Maggie.
I'm kind of confused because the other bullet point said they weren't, esters can be acidic. So I don't know why I'm confused about it it's saying acid. Like this, is that even part of it? Or
Are you talking about this part right here? Like this part is from acetic acid?
yeah, like how is it still a S? Is it still an ester if I don't know. Oh yeah, I'm just
I get what you're saying. So this is not acetic acid, okay? What they're doing is they're taking this part that's highlighted in blue and they're saying, okay, how do we name this part? So again, esters are always formed from carboxylic acids. So the carboxylic acid that looks very similar to this is this right here. This is the carboxyl group. That's what makes it a carboxylic acid. That is acetic acid. The common naming for this carboxylic acid is acetic acid. So what they're doing, Maggie, is they're taking, I'm going to highlight in a different color. They're taking this part right here. This is the part that's the same. You see how that's the part down here that is still highlighted in blue? And they're saying, okay, we're going to call this acetate. It looks a whole lot like acetic acid, but this part right here, this OH group is no longer an OH group. Now it's an ester. Now it's an OCH2CH3. And they're naming this alkyl group right here. That's an ethyl group. That's where the ethyl part comes from. And they're keeping the name similar since the root part of the parent compound is similar to acetic acid. They're just naming it as an ester. So it is not an acid anymore. It does not have acidic or basic properties. Which part, if I zoom in on acetic acid, which part makes it an acid? Which part did we say is the acidic part? Does anybody remember? We said carboxylic acids are weak acids. They can give or receive a hydrogen. It is this part of acetic acid that makes it a weak acid, okay? We don't have that hydrogen down here anymore. That's been ripped off, and now we have an ethyl group in its place. And that's what makes it an ester, okay? So the fact that they're saying this is from acetic acid right here is just because they're considering the part highlighted in blue and they want to keep the name the same since that looks like this part right here.
Okay, that makes sense. Thank you.
Okay. Any other questions on how we name? I think I've got a practice problem. We'll practice naming esters. Right here. So, what is the structure of butyl acetate? Okay, so let me erase because you actually have ethyl acetate here. Look at that. Consider how is butyl acetate going to be different and try to draw butyl acetate. So you should have the acetate part is the CH3, C, and then, oh, there's the ester, the carbon, oxygen, and then to another carbon, but instead of an ethyl group, you should have a butyl group. We know butyl is 4 carbons long. Okay, so here is my butyl group. So this is butyl acetate.
Would it matter which side you drew your butyl group on?
Mm-hmm.
Okay.
It has to be on the other side of this oxygen. So if you try to draw the butyl over here, that's butyric acid. So that would be
when I read butyl first, like that's the first thing I drew.
So for example, what Madison is saying, guys, she did this CH3, CH2, 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 and then CO, and then O, CH2, like this. You see how these are kind of opposites of each other? The carbon substituents are just reversed. Let me scoot this down. Okay, so we have the methyl here versus here, and we have the butyl group here versus here. So there's 2 different names for this. The bottom one is butyl acetate. The top one is methyl butyrate. Because you have butyric acid, you change the name ending to ATE because it's an ester, and that's the methyl group on the ester side. So butyl acetate is this one right here.
Thank you.
Uh-huh. Okay, let's try some more. I went ahead and put table 17.1 on this slide. I don't think y'all have it on your slides. I threw this on this morning just so y'all could see it. So I'm gonna zoom out so y'all can see those. Hexyl benzoate. Okay, so again, here is benzoic acid. That's the root compound here. Now, instead of an O8, whoops, what happened, Robin? Okay, I'm good. Instead of the OH right here, we're gonna have a hexyl group. It's gonna be an ester. Make sure you draw in the ester part. So I'm gonna start drawing this. Okay, so we got the carbon, double bonded to the oxygen, and here's the ester part. Now I need to draw a hexyl group. A hexyl is just a 6 carbon substituent. And how do you know how it's added on? It should be through the end carbon, one of the first or the last carbon. It would have a totally different name if it was like from an internal carbon. So CH2, 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 1, 2, 3, 4, 5, CH3. Okay, or you could draw the line structure, it would be a lot quicker. So if you did the line structure, C double bond O, O, and then 1, 2, 3, 4, 5, 6. Okay,
Branching that off, does it matter where it's placed? Well, not, like, could you have connected it at
you
the
could
bottom?
have
or-
connected this part to any place on the aromatic ring, Maggie. When there's just one substituent, all the carbons on the aromatic ring are considered identical. So it does not matter where you branch it from the aromatic ring. Okay, methyl formate. Anybody got the structure for methyl formate? So you're looking at the common namings. Formate is the ester form of formic acid. So formic acid is actually the most simple carboxylic acid there is. You got the carbonyl group, you got a hydrogen. We don't even have a carbon group on the other side of this. And then we've got the O is what makes it an ester here, the single bond to the oxygen. And then we've got methyl. Y'all know what a methyl group is. That is methyl formate. Questions on how I got that? Okay, ethyl, this one's a weird one, acrylate, ethyl acrylate. So that comes from acrylic acid right here. I just think of acrylic paints though. So you're gonna draw this, make it into an ester, and add ethyl to the other side of it. So I'm gonna zoom back in on this. Which carbon in here? This one, let me number them. 1, 2, or 3. Which one is the carbonyl carbon?
Is it number? Ooh. I don't know.
Is it number 3?
Mm-hmm. Number 3 is that's the one double bonded to an oxygen. This portion right here, this is your well, yeah, do that. This part right here, this is your carboxyl group. So focus on that. I'm going to draw that first. That's carbon 3. Now I got to draw the rest of this on the left side of that the same. So I've got a bond to a carbon. So this is carbon 2 that I just drew. I see that carbon 2 has one single hydrogen and then it's double bonded to a CH2 group. So I'm going to actually draw this over here. We have CH2 double bonded to C, and it's got an H, and then this is the COOH. So that is acrylic acid. We've got to make this into an ester. So I'm going to keep this portion of the molecule the same, and I'm going to change that part. Okay, so I'm going to draw this all the same. So I got a double bond to CH2, and then this has a hydrogen. Okay, so that part's all the same. Now to make it an ester, I just single bond that to an oxygen, and I add ethyl. Okay, so, whoops. This part right here is ethyl. And this portion right here is acrylic acid. But we call it acrylate, ATE ending, since it's an ester. Okay. So far we have covered today carboxylic acids, how to name them, how to identify them and their properties. Now we've talked about esters, briefly hit their properties and have practiced their naming. Now we're going to get amides, look at their properties, name them, And then we'll see how much time we have left after that. Okay, amides. So here I'm going to zoom in on this group. Here's the carbonyl carbon. An amide sounds very much like an amine. Yesterday we talked all about amines, which are groups that have nitrogen in them. An amide is an amine group bonded to a carbonyl carbon. Okay, so here's the amine portion. It's actually an amino group. NH2 is an amino group bonded to a carbonyl carbon. The only thing is we can have wildly different kinds of amides. So right now you see that both things bonded to the nitrogen, branched off the nitrogen, are hydrogens. Those can be so many different kinds of groups. Okay, for example, let me scroll over down here. That's a primary amide. You could have secondary amides or tertiary amides, where you have only one hydrogen bonded and then some kind of carbon group, or you can have no hydrogens bonded and two carbon groups bonded to that nitrogen. Okay, so you can, and then here's all the condensed structures for that. This is your carbonyl portion, and then here's the primary, secondary, and tertiary in those condensed structures. Okay, so they can be wildly different. Don't just think it's always NH2. All right, but before we get into the rest of the slide, remind me, how are, you guys tell me in your words, how are amines and amides different? In the simplest way, how could you explain that?
Amines have the double bond to the O.
Amines are bonded to a carbonyl carbon, and that carbonyl carbon is double bonded to the oxygen. Okay, so amines, no carbonyl group. Amides, the nitrogen is bonded to a carbonyl carbon. Okay. Can y'all read my handwriting? It's kind of rough sometimes. Amines have no carbonyl group. Amides, the nitrogen is bonded to a carbonyl carbon. Okay. Now we're going to get into properties just a little bit. So I have another difference here. I have this statement: unlike amines, amides are not basic. Okay, why? I'm going to draw something like what you see right up here. I'm going to draw this again. C double bond to O. I have some kind of R group, and then N and H and H. And we know the nitrogen, when it has 3 bonds, has a lone pair. So there's a few things to point out. Actually, I'm going to go to black for a second. This oxygen is very electronegative, right? We know that about carbonyl groups. That also means this carbon is very electropositive, because all the electrons in these bonds are drawn towards oxygen. They're pulled towards oxygen, all those electrons. So that's why we say, I'll redraw this, that this carbon is partial positive. So guess who is aware that they are bonded to a partial positive carbon? Nitrogen is. Nitrogen is also a pretty electronegative element, and it has a lone pair. So these electrons right here, these are very aware. I'm going to draw a double arrow here, and I'm going to highlight this double arrow. These are very aware that they're bonded to this partial positive carbon. There's an we know opposites attract. Okay, these electrons have a lot of negative charge, right? And they see that partial positive carbon. So these electrons, the reason we're saying amides are not basic, we said amines can act like bases. Yesterday, we even looked at acid-base reactions where amines act like bases around water or other acids, and they accept a hydrogen. Amides don't do that. So these electrons do not accept hydrogens. That's why we're saying amides are not basic. They are already attracted to, they already got their eyes on somebody else, okay? They're not available. They're not on the market. They don't want to bond with anybody else. They're already attracted to the carbonyl carbon. That makes sense? Okay, I hope that makes sense. All right. Hydrogen bonding, that's another thing we always have to talk about. Primary amides can do very, very extensive hydrogen bonding. That's exactly what you see here in this figure. All of these red dotted lines, these are all different ways that primary amide, this is a primary amide, this is a primary amide. It's only bonded to one carbon, so that's why it's primary. So we got all these positively polarized hydrogens. These are all donors. And we always have a lone pair. We got these oxygens that are electronegative too. These lone pairs also have, these nitrogens also have a lone pair. Those can hydrogen bond as well. Oh, no, I'm sorry. That's a mistake. We just said these lone pairs don't interact with hydrogens, okay? So just consider the figure when you're thinking about how they can hydrogen bond. All right, therefore, because of all this hydrogen bonding, their melting and boiling points are higher than their corresponding acids, meaning corresponding carboxylic acids. Okay?
I have a question.
Yes, Maggie.
Does it matter which one? Because there's two different, I guess, situations where it's an O double bonded to a C than a nitrogen.
On this figure?
Mm-hmm.
Yeah, this is two different amides. So let me highlight one. All of this right here is one amide, and then I'll highlight in blue. This is a different amide.
Oh,
They're just turned
Okay.
different ways.
okay.
And then they're just hydrogen bonding with one another.
Okay, thank you.
So you can get hydrogen bonding through the electronegative oxygen and the partial positive hydrogens on the nitrogen. Okay. Because of all that hydrogen bonding, to see the effect of how that affects to see how this property affects boiling points, I threw this little figure in straight from your textbook. So what is this figure doing? It is comparing, this is a straight carboxylic acid. This is acetic acid. Why? Because you have this OH group bonded to the carbonyl carbon. That's carboxylic acid. And you can see its boiling point right here. Okay. Now we have a primary, a secondary, and a tertiary amide. And look at the boiling points compared to the regular carboxylic acid. They're like almost double in some cases. And they're always for sure higher. Okay, so that is why this figure right here is reinforcing what I just said in this gray text box up above. That amides, whether they're primary, secondary, tertiary, doesn't matter. All the extensive hydrogen bonding they can do makes their boiling points way higher than these similar carboxylic acids. Okay. So if I ask you on the exam, which has a higher boiling point, carboxylic acids or amides? You would definitely tell me amides. Or if I ask you to order, gave you two different molecules and asked you to put them in order of their boiling point, you would always put amides with higher boiling points. Okay, how do we name amides? We name by replacing the ending instead of ic acid or oic acid. We name the carboxylic acid and we just throw the word amide on it. Pretty simple there, pretty straightforward. So if the nitrogen on the amide group is substituted, what does that mean? If it's got like methyl or ethyl groups, you're going to treat it the same way we did yesterday with amines. You'll say in methyl or in dimethyl or in ethyl. Okay, we introduced that yesterday. You name the substituent alkyl groups and then you name the amide. Okay, you name the substituents first. Those are like the prefix words, and then you name the amide. Okay, alkyl substituents are preceded by the italicized letter N. That's what we did yesterday in chapter 16. That's indicating to us when we read that naming that those groups are bonded directly to the nitrogen, if you see an N. So let's look at an example. If we have acetic acid, but instead it's an amide, we just call that acetamide. We just take the ic acid part off and we put the word amide on. You'll hear people pronounce this acetamide. So instead of acetamide, you'll hear us say acetamide. They kind of flow the word all in one word. Acetamide, okay? Okay, so this is benzoic acid if it's a carboxylic acid, but it's not. Now it's an amide. So instead of benzoic acid, we call it benzamide. That is the root parent amide since it is a, whoops. Since it's an amide, I meant to erase this. But now we have these, okay, it says there's 2 methyl groups bonded to this nitrogen right here. You see the arrows pointing to this. So we're going to call it NN. Each one gets its own italicized letter N, just like each substituent would get its own number, 1,1 or 2,2 dimethyl. And then we say dimethyl benzamide. Okay, that's all the examples I'm going to give you for naming amides. I think we'll do a practice, but I'm not going to grill you guys on how to name amides. I want you to know these rules. I might give you some simple ones. I think there's probably some practice from the recommended textbook problems or on the homework. But we really did a ton of practice with like the alkanes and the alkenes and the aromatics. By now you should have a lot of those rules down. And so here we're just throwing the word amide on the end, and we're still using a lot of the rules that we have implied from previous chapters. All right, this is a little bit of a review slide because we've covered a lot at this point. So to review, you see a bunch of different molecules. What's similar, what's the same in all of them is what I'm going to highlight. This carbonyl methyl, carbon. This is all the same. The part that's different is the part that's red. Okay. So I hope you can learn how to look at these. Identify the carbonyl carbon and then see how it's customized or how it's tailored. We always kind of write it off to the right side. Okay. I think that'll help you if you always orient molecules like that. Like the part that's changed and tailored, whether it's an amide or an ester, is branched off of the right side of the carbonyl group. It doesn't have to be, but it just simplifies things when you always draw them that way. Helps you see it in your head easier. Okay, so this first one is an ester, right? Methyl acetate. We walked over rules for how to name that. We have the ATE ending because it's an ester. This one's acetamide, okay? It's a primary amide. Here we've got a methyl group bonded to this nitrogen, so it's N-methyl acetamide. Okay, what if we have 2 methyl groups bonded off that nitrogen? N-dimethyl acetamide. We just looked at that on the previous slide, but with benzamide. You know why they call this a tertiary amide? Can you look at that? We've got 3 bonds, one right there, and one right there. 3 bonds to carbon. So that's why it's a tertiary amide. Yesterday we learned how to classify amines. It's the same principle here with amides. You're looking at how many carbon bonds this particular nitrogen is bonded to. How would we name this one? We've got an ethyl group and a methyl group bonded off our amide nitrogen. So that's N-ethyl, N-methyl. And you, again, alphabetical priority here. Ethyl comes before methyl. N-ethyl, N-methyl acetamide. I bet you can fill in these blanks. Okay, this is just review. So esters and amides are made from, or you'll hear me say they're derivatives of carboxylic acids. Esters and amides can be converted back to okay, we haven't talked about this yet, via hydrolysis. So this is actually not, that part's actually not reviewed. We're going to get to hydrolysis reactions. All hydrogen bonds, tertiary amides. Oh, sorry, all can hydrogen bond. But tertiary amides can only hydrogen bond with donor molecules. So you might consider how that would affect their boiling points. Tertiary amides would have lower boiling points than primary, secondary. What do y'all think this next blank is? Carboxylic acids are weak acids. What about esters and amides? They are neither what?
Is it acidic or?
Yes, Maggie, they are neither acidic nor are they basic. And then small esters and amides are marginally water soluble. So talk about things you might want to throw on your note card. If you just want a quick review to help guide you on the exam, I think these overall points, you could probably write your answers or guess the right answer from these quick statements here. Okay. What we'll probably do is do this practice problem, and then we kind of move on to a different topic. So I'm going to wrap us up early after this. We're going to do this slide and we're going to take a break. And when we come back, we'll finish our slides. Let me see. We are right. So that would leave us with 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, a lot of slides, but I think we need a break after this. Okay, so what are the names of the following compounds? So we need to be able to classify it before we can even name it. So somebody tell me, I'm gonna wait on y'all. A, what is A? Is it a carboxylic acid, an ester, or an amide?
Is A an amide?
Yes, it is. It is an amide, so how would we name this? It's an amide because of this right here. Bonded to, here's my carbonyl carbon. So you can do the common or the systematic naming here. If you're wanting the quick common name, you might want to refer back to this table right here. There are 4 carbons in the chain starting with the carbonyl carbon. So what is our common name for that? It's gonna be up here.
Would it be alpha bromo butyric acid?
So yeah, we are gonna grab butyric acid here. That's the parent carboxylic acid, but it's an amide, but we're still gonna use the parent name. So the reason I said I circled butyric acid, we got 1, 2, 3, 4, okay? So, Madison, what did you say?
Would it be alpha bromo?
Yes. Okay, so this would also either be carbon 2 or be alpha, the alpha carbon. Alpha bromo, how do we finish this? And before we even get to that, we've got to name this part right here, right?
Is it an N-methyl?
Yep. N-methyl, alpha bromo, then what?
Why did we put the N before the alpha?
Because when you're naming amides, you name the substituent off the nitrogen first, then you name the portion derived from the carboxylic acid. You always name this part first. whatever's branched off your nitrogen. If there are any substituents. If it's NH2, you don't have any substituents to name. But if there is an alkyl group branched off the amide nitrogen, you got to name that first.
Would the ending be is it butyric?
Whoops, I'm on highlighter. So BUTY, I think there's instead of butyric, it'd be butyramide.
Okay.
See, just the way we did up here. When we have an amide, instead of acetic acid, it was acetamide. You take the ic part off and you put the word amide on. So we just take, instead of butyric, whoops. We take the ic part off and we put the word amide on. See that? So this is a crazy name, N-methyl alpha bromo butyramide. It's even hard for me to say. Okay. We've got two substituents off of the nitrogen here. So this is another amide, right? So you're going to name those substituents first. Then you're going to look at your parent compound here and name that. If anybody thinks they have it, don't be afraid to be wrong. But I bet you'll be right. Again, if you have trouble naming this part right here, go back to table 17.1. I'm going to scroll up so we can look at that. This is table 17.1 in your textbook. So we have a derivative of this carboxylic acid right here. It's not a carboxylic acid, but we have a portion of this molecule made into an amide. So we'll need this root parent name, everything but the ic. We'll substitute the word amide in place of the IC part, ic.
I think I might have it, but I don't know.
Okay, tell me, Abby.
So what I put was N-ethyl, N-methyl, and then benzamide.
N-ethyl, N-methyl, okay.
Benzamide.
Look at you. Anybody agree or disagree? Yeah, ethyl. What, Robin?
Oh, I just said I agree.
Great. Except for, yes. You take the OIC off on benzoic acid and it's benzamide. Yep, that's perfect. So ethyl comes before methyl. You put the N in front of both. N-ethyl, N-methyl, benzamide. Okay, C almost tricked me earlier when I was looking at it. Anybody think they have C? This is another amide. So you need to number the longest carbon substituent, starting with your carbonyl carbon. When I do that, I get 1, 2, and then I do, and then you got to go down 3, like that. You need to number it that way. I was tempted to name this as carbon 3, but you really run into issues trying to name this hydroxyl group. Either way, both are carbon 3. Well, yes, both are technically a third extension, but you need to go down and name this one is carbon 3. And then this naming the substituents becomes exponentially easier. Anybody have the name for this?
I'll try it.
Okay, Maggie. Maggie's got it.
Is it alpha methyl gamma hydroxide?
So it should be beta. So this
Beta,
would be
okay.
the alpha, and then this would be the beta carbon. And the only other thing, Maggie, you're exactly on the right track, but I'm gonna scoot this one over and we're gonna write hydroxy before methyl. So I like what you had, okay. Whoops. Okay. Beta, try this, beta hydroxy, alpha methyl. And then how do we finish this out? We're doing hydroxy first because it has alphabetical priority. So how do we name the rest of this?
Would the ending just be propamide?
So instead of propane or propanoic acid, what did you say, Robin?
Propamide or propamide, however you want to say the amide part.
You're missing one syllable, propanamide.
Propanamide, okay.
So instead of propanoic or propane, it's propan, A-M-I-D-E, propanamide. You were all over it though. Okay, wow. This is not easy stuff. These are complicated names. So this will need some practice for sure. I got another practice problem. We're not going to do it right now, but this is just to classify it. Look at these different structures. A lot of them are just written as condensed structures, and then classify, is this carboxylic acid, ester, or amide? But we're going to take a break, and let's come back. What time is it? 10:26. Let's come back in 20 minutes. So 10:45. Okay. I'll see y'all then.